Find the minimum value of the function f of p. In this problem, we've been provided a function f of p, which is represented by the violet surface in the three-dimensional plot, where the value f of p depends on variables x1 and x2. The problem states to use the method of steepest descent and provides the equation for successive points p, used to find the optimal point p, which will minimize our function f of p at p star. We've also been given the starting point of the algorithm p0. Also note that variables x1 and x2 are unbounded or unconstrained, which means this is an unconstrained nonlinear optimization problem. It would be easiest to describe the method of steepest descent if we drew out a contour plot of the function f of p, which looks down on the x1, x2 plane. Next, we'll locate our initial point p0, which is our starting point. Then, for each iteration of the method of steepest descent, we'll move from Pn in the direction of steepest descent from point Pn by a distance alpha n to the next point Pn plus 1. Then the process continues until the gradient equals 0, which means we've found our minimizer, p star. To begin, we'll compute the gradient of f of p, which equals 2 times x1 minus 4, 4 times x2 minus 8, which makes the gradient at our starting point, 0, 0, equal to negative 4, negative 8. Therefore, we'll want to move from point p0 in the direction of the negative gradient 4, 8. In the search algorithm, the vector 4, 8 means we will traverse 8 units in the x2 direction for every 4 units in the x1 direction from our initial point p0 to our second point p1. In other words, x2 minus 2 times x1. In 3 dimensions, this is the equation of a plane, since the dimension f of x is unspecified. The intersection of a plane and a curved surface is a curved line, which we can solve for by plugging in 2 times x1 for x2, which results in a quadratic equation of variable x1. This quadratic equation has a local minimum at negative b divided by 2a, which equals 1.111, and makes x2 equal to 2.222. Now that we've found point p1, we'll compute the gradient to find out if p1 is a minimizer. The gradient at p1 equals negative 1.778, 0.889, whose opposite direction is positive 1.778, negative 0.889. Therefore, from point P1, we'll travel 1.778 units in the x1 direction and 0.889 units in the negative x2 direction, a distance of alpha 1, to reach our next point, P2. Point P2 is much closer to our minimizer, p star. As with the previous iteration, we notice the direction vector is equivalent to a plane. This time, the equation x2 minus 0.5 x1. However, we're not interested in the plane that passes through the x1, x2 origin, as we were before. We're interested in the plane which passes through the point x1 equals 1.111, x2 equals 2.222, which computes to x2 equals negative 0.5 x1 plus 2.778. To find the quadratic equation that we want to minimize, we find the intersection of this plane with the curved surface of f of p, which simplifies to 1.5 x1 squared minus 5.555 x1 plus 1.214. Therefore, the minimum value of x1 equals 5.555 divided by 1.5, or 1.851, which makes the corresponding value of x2 equal to 1.851. If we take a step back, we began at point P0, which was at 0, 0. Then we moved to point P1, which is located at 1.111.2.222. From there, we moved to point P2 at 1.851.1.851. If we compute the value of the function f of p for f of p0, we get 8. For f of p1, we get negative 3.11, and for f of p2, we get negative 3.93. If we continue this algorithm for points p3 and p4, the values of the function evaluate to negative 3.99 and negative 4.00. Therefore, as our point approaches 2, 2, the value of our function f of p approaches its minimum value, negative 4. When reviewing the possible solutions, the answer is A.